today we're going to be talking about non-right triangles. Okay, but the first thing I'm actually going to have you do is use your knowledge of right triangles and SOHCAHTOA, or Pythagorean theorem, to answer questions 1 through 4 on your practice. And then we'll go over how we can use that to develop properties that work for non-right triangles. Okay, so pause the video and try those 4 for me, please. Okay. There were 2 right triangles that appeared in this first one, which means there were 2 versions of this sign, SOHCAHTOA, that we could have used. And both of them are going to give us the exact same height, this value in the middle. Now, as a reminder from geometry, by definition, these were right triangles because a height or an altitude of a triangle is the piece of the triangle or the part in the middle or outside that touches the base at a right angle. So we know those were right triangles, so we can use SOHCAHTOA. And from there, I was just asking you to go back in terms of B and C. So if you had down here still with the numbers, we're just going to look back at those. So this 5.41 on the triangle was B, so we'll use that. This 68.2 was the angle C, so that first part looks like B sine C, or it could have been maybe the second one that you did. And then over here, the 7.1 was the C value from the triangle, and the 45 degrees was angle B. And this is actually very similar to what we're going to talk about today, the law of sines. Okay, the law of sines that you're used to seeing doesn't look quite like this. So we'll get to the version it does look like here in a bit. You have a space for it below number 4. Okay, you were doing the same process on part A for number 3. You have to focus on a right triangle in order for SOHCAHTOA to apply. So hopefully you recognize that this big triangle on the outside works for us without finding any extra angles. I did have some people who solved for some missing pieces to focus on a different angle. But when we're finding the height, it is this side here, and that is the part of this larger right triangle. So we can use sine of 20.6 and x over that 8.5, the hypotenuse. I do want to emphasize that this hypotenuse is only called that because we're dealing with a right triangle. If I were to focus on this obtuse triangle, the one that's shaded in blue here, for me, that would not be the hypotenuse. It would just be the side that's opposite the 123.7 degree angle. Okay, so we can only call it hypotenuse with right triangles. But then from here, you have to multiply by y. Once we got that side of the 2.99, we can set it up. And this one, if you struggled solving for it, it's because we have to move the y out of the denominator. We can't divide by that 2.99 because then we're left with 1 over y, not just y. And then that we can divide over, so this 2.99 is on top. Okay, so 3.59 was our missing link here. And that's what we're going to use to determine whether that equation still applies. So again, these letters are from the triangle that was shaded, not from this height that wasn't part of the triangle. Okay, these are imaginary pieces so that we can visualize that perpendicular value, the altitude. So from there, B is literally this 8.5. Sine C, C is the angle C 20.6. And on the other side, you have to use these 2 numbers. You can't use the 90 and that other value that we solved for. This C is the side across from this angle on the triangle, not the height, so 3.59. And then it was sine of that 123.7. And those were approximately equal. They weren't perfect because we have some rounding error as we went through here, but they are equivalent. Now I'm going to show you the version of law of sines that you've seen. And it comes from taking this and just moving some stuff around. I can divide the B over, and then I can divide the C over the same way. So you've seen something like sine of C over C is equal to sine of B over B, and then sine of A over A. The letters are not what we need to focus on. Instead, what we need to focus on is the relationship in the triangle. we can use this formula, and what we're going to do today, we can use this formula if I know some pieces of information. So I have one side and one angle that are across from each other. And then if I need to find other information, in this case, the real goal was this part B. I wanted to find out what this side here was. And before we talked about non-right triangles, you had to take a step to find that by getting the height. And so now what we're going to do is skip that height step, and we're going to use just this information to solve, and we can do that if we have two pairs of sides and their opposite angles, where one of those pieces of information is our variable. So in here, what I want to indicate is you have two pairs. Okay, we're not going to have three pieces ever, it was just two. And all you need to do is be able to pair up x with something across from it and have one other pair in the picture. Okay, sometimes it's going to be beneficial for us to write this with the sides on top. This is equivalent and valid. And what we're going to do usually to set this up to make our life a little bit easier when we're solving is always put the variable that we need on top. That may be a side or it may be an angle. So we're going to start out by just labeling side B, that's this one, and we're going to look for pairs. So across from B is the angle 22, and we have to have another pair in the picture. Now we have an angle and a side, which is good, this 118 and this 24, but they're not across from each other, so they wouldn't actually pair up. Now, it's not possible for us to find this missing side without more information. So we have to pair up with this 24 because it is possible to find this angle pretty easily. Okay, when we're thinking about angles in a triangle, they have to add to 180 degrees. So if you add those two together, you get 140. There's 40 left over. Okay, so for the math, we would set it up, since B is our variable, I'm going to start with it. And sine will always go with the angle. Since B is a side, we don't need it there. We're going to need it on the bottom with the 22. And then we pick on our other pair, keeping the side on top and the sine of the angle on the bottom. And setting it up this way allows us to solve just in one step. Okay, when we see proportions, we like to cross multiply, and you're welcome to do that. But if you set it up with the variable on top, you really only need one step to solve. And you don't have to write this, I'm just showing you so you can see it. All we have to do is multiply that sine 22 over. Now when you type this in, you do have to be careful. What we know about our calculator is when it types in sine, cosine, tangent, it's going to open parentheses. So as you go across here, 24, sine 22, it opened the parentheses for you. You have to either close it before dividing or just hit enter. If you forget that step, you may come up with an answer that's not reasonable. So we're always going to check in our last step if our answer is reasonable. That's about 14.0. By placing this on my triangle, I can check if it lines up with the other numbers that I do have. We know from geometry that a large angle is going to be across from a large side, and a small angle is going to be across from a small side. So we just have to check that out. From 40 and 24, our 22 is smaller, so we should have a smaller number than 24, and we do. Now you'll notice I put units on there. Right? We're going to get in the habit of labeling those, so when we get to word problems and they attach centimeters or inches or feet, we remember to put that on there. Okay. Next one is similar. We're going to find an angle measure this time, but we're going to just put that in the picture first. We're trying to solve for C. So we pair it up, and we look for a second pair. And I say we look for a second pair because starting next time we're going to talk about triangles where maybe the law of sines doesn't work. So we're going to try this first, and if it doesn't work, then we'll move on to the other option. So in this case, we do have another pair, nothing's missing. We can go straight to work. So since we're solving for an angle this time, sine is going to go on top with that C, and we'll just put a regular 20 on the bottom. And then it's equal to sine of the 82 over the regular 29. Still solving for C, so I can move that 20 over. I like to put it in the front for these ones just because extra parentheses can be avoided that way. So that is 20, then sine 82. Okay, we have to close it again or hit enter before dividing. And there's just a regular 29 on the bottom. Now this is pretty messy, but I'm going to write it down so we can see what's going on. I hope you recognize that that is probably not our angle. Okay, it seems very, very small to be an angle, and it's not in radians, we're in degrees, so that seems strange. But remember, that is not C yet, it's sine of C. So we have one last step. To solve for an angle, we have to use the inverse. So we're going to use inverse sine of that value. And I don't care what you round to here if you're writing it down, because we're going to use the whole value from our calculator when we go get it. So second answer, we'll bring it back up. And then our angle itself is about 43.1. And that'll be in degrees. We're going to check this one the same way we did the last one. If I put 43.1 degrees, we want to line it up and make sure that's a number that seems reasonable. And because 82 is our biggest angle with our biggest side, we're seeing a smaller angle with a small side. It works out. Okay. All right, I give you a little bit of information here, but what I want you to do for me is solve for angle B, just like we did on that last one. And then I want you to read that information and think about what it's asking. Okay, try that problem and then come back to the video. Okay, for solving for angle B, no problem to set it up just like the last one. We've got sine B over 62 equals sine 58 over 54. And we're still going to have to use the inverse for our last step. Which is 76.8. But the instructions here told you that if you're solving for an unknown angle, there may be two angles that satisfy the equation. The equation I'm talking about is this one. The sine of B that we got was this 0.97 value up here. If we think about the unit circle, 0.97, a positive one, for sine could happen about here or about here in two different places. Now remember from what we did last time, when we use the inverse sine, that's an expression that only has one answer from your calculator, and it's giving us this value. But this value could also be a solution to our triangle, because remember, angles in a triangle can be obtuse, which means they could be as large as 180 degrees. Okay, not 180 itself because we have to allow for the other two angles, but they can be fairly large as we go through here. So what we're going to do always when we're using sine inverse, because our calculator is only giving us quadrant 1, is we're going to find also the supplement, because that's the relationship between these two angles here. If this was 30, this would be 180 minus 30. Okay, here our angle is 76.8. We're just going to take 180 minus that to get the other answer. Okay? And in the case of this, I want to really emphasize it doesn't have to work. So we're going to write an or, this 103.2 degrees, and we're going to check if it would be reasonable. So I know this first one is going to work out, this 76.8. As long as I did my math right, it's going with the bigger number. That's all good. But we're also going to check if the second one would work. So if I put a 103.2 here, it's still the larger angle, so that still works. And the only other thing we're going to check for is making sure that putting in this obtuse angle doesn't make our triangle impossible by having angles that add up to something larger than 180. So because this 103 plus the original 58 doesn't go over 180, this actually is a possibility. Now, how this would work, because it seems like for this one, obviously B is not drawn as an obtuse angle, but pictures don't have to be drawn accurately. This B, because we don't know what the angle is, could slide in and out, because this 54 isn't set in stone by some angle up here. Whereas this 62 is defined by this 58-degree angle. These two sides are rigid and they cannot move. But this 54 can move around. So I could have drawn this 54 going this way instead. My 62 is still longer than that. And I can still make a reasonable 58-degree angle. And that's really where that 103 is coming from. Okay? So we're going to check the angle and its supplement every time that we're solving for a missing angle. It won't always work, but we'll always try it. Okay, so let's look at this next one. We're going to draw out the picture since it wasn't given to us, but we're supposed to find all possible solutions for the missing values given the information. So you don't have to draw these accurately because our diagrams don't have to be perfect. We'll just check that our numbers are reasonable for their locations. So just sketch any kind of triangle you want that's big enough for these values to go in and on it. Okay, we've got an R, so we're going to label one of these corners R and call it 60 degrees. Then little r would have to be across from it with 47 feet. And then they give us another side that's 51, and they don't tell us which one it is, so it doesn't matter. Pick one. Okay, but if that is S, then large S would go across here. And that's going to be what we have to solve for first, based on the information we're given. We don't know that this is the right triangle, so we're using law of sines. So we've got sine of S that we're solving for over 51 equals sine of 60 over 47, and we can solve that in our calculator. Multiplying the 51 over first, and I like to throw it in the front. You don't have to as long as you're careful. Hit enter or close your parentheses before dividing by that 47. Remember, that looks like a decimal because we're not done yet. Okay, we have to now take the inverse of that, grab your answer, and we've got an angle of about 70 degrees. Okay, so that is one option, but what you need to get in the habit of is writing or anytime you're doing an inverse sine. We don't have to worry about that with inverse cosine because cosine already allows second quadrant values to pop out. And we're not going to have to worry about with inverse tangent because the only type of triangles you'll use an inverse tangent are right triangles. And if it's a right triangle, we can't have an obtuse angle anyway. So our supplement is going to be about 110, and we're going to check that these things work. So if I put a 70 degrees here, then I'm checking that my biggest side goes with my biggest angle, and that's working out. I'm checking that when I put these angles together, I'm not going over 180, and I'm not. So for this one, I've got 60 and 70 is 130, so there's 50 left over for that missing angle. And we're going to draw a picture for both triangles since this one may work as well. So I'm going to draw a second one here. Same original values, the 60 degrees, the 47 feet, the 51 feet. But this time I'm going to check the 110. Okay, so big side is across from, this got a little ugly there. Big side is across from the big angle still, and the smaller side is with that. When I put these together, I get 170. There is still left over 10 for this triangle to be possible. If I was drawing this realistically, this 51 would still be going this way. Here would still be a 60 degrees, that's rigid. But this 110, in order for it to work, would have to go this way. And in order for this number to work, we'd have to have this go really, 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 really long for that 10 degree angle to show up. Okay? That's a big reason why I'm not having you spend the time to draw them accurately, because sometimes those angles, when they get super obtuse, are really difficult to draw where you can actually fit the numbers in there still. Okay, but I want all of the missing values, which means I have two things left. This bottom side over here, we don't have a letter, so you can pick whatever you want. And then this side over here, because they're across from different side angles, they will be different sizes. So on this one, I can solve for it using law of sines. And it will just be an approximation because that 50 is rounded. That's the best thing we can go with. I'm going to always use this 47 over 60 or whatever information was given rather than the other pair where I solve for something. That way if I mess up this one, I won't mess up the other one as well. Okay, and then solve it using that. So 47 sine 50, hit enter or close your parenthesis, and then divide by that sine 60. Reasonably, our number should be smaller than these two, but probably not by a whole lot since 50, 60, and 70 are relatively close together. Ours is about 41.6. And we're going to label it feet. Now we're going to repeat this process over here with this triangle. Call it y. And that's y over sine of 10 equals another pair again. I'm going to use that one. So 47 over sine 60. You'll notice that the only thing different about these two equations here is this value. So a lot of times I won't even write it twice. I'll just write that 10 below and look at that same value. So here we're taking 47 sine 10 this time and still dividing by sine 60. A reasonable number for this, again, smaller than 47, but it's probably quite a bit smaller than 47 because this 10 is so small compared to the other angles. This one's about 9.4. And those two triangles have all your final answers on them. Okay. What I'm going to have you do is pause the video on number 8 to finish that one. Try it on your own. Look at your example here. Remember, if you're using law of sines, okay, and you're solving for an angle, there's that second possibility that you have to check. Okay, so try that, and then come back for us to chat. Okay. This one, hopefully you noticed that this was a right triangle. If you didn't, we can still use law of sines. It would have looked like sine of, we were solving for u, over 56 equals sine of 90 over 70. But y'all, if I'm solving for this and it's a right triangle, I can just as easily say sine u equals 56 over 70 and use the inverse from there. Now these are exactly equivalent because if I look at this, 56 is still on top, 70 is still on the bottom, and sine of 90 is 1 from our unit circle. Okay, so it's still okay to use law of sines. If you are using the law of sines, I want to see the or, so 53.1 degrees or, but the reason we didn't have to do this check when we were doing the inverse sine on right triangles is because if this is a right angle here, 90 degrees, and the supplement is always obtuse, I can't take a number bigger than 90 and add it to 90 and have it work in my second triangle. So that does not work. Okay? Once you have that angle, you can subtract from 90 to solve for the missing angle up there. And because this was a right triangle, you could have used Pythagorean theorem, x squared plus 56 squared equals 70 squared, to solve for that missing side down here. Or you could have used SOHCAHTOA. Again, if you didn't catch that and use law of sines, it does work. Just make sure that you get labels on your final answers. So all of these should have yards, and the inside pieces should have angles. Okay. Last thing we're going to do is talk about area of a triangle. Hopefully you remember from geometry, triangle is 1/2 base times height. With remember these two have to be at a right angle. Okay, so before I set you loose to try this one, I'm going to emphasize that the height must be at the right angle, so you need to look for that first. And the base is the thing that intersects it. So those are the two pieces that have to go in this formula. I give you some information. You're going to have to solve for some information to be able to answer this question. Okay, so I'll let you try that, and then we'll chat. All right, so here, with looking at the right triangle, okay, this was not like the front side. You don't have two options. You can't use this triangle or this triangle. You can't use this 6.7 or the 7.6. This right triangle here, this side, we don't know. This whole thing is 6.7, which means we're going to use it in our area, but we can't use it to solve for the height because it's not part of our right triangle. We have to use this. So from it being a right triangle, we've got opposite side and the hypotenuse, which means we can use sine of 28 equals opposite x, you could have called that h, over 7.6 to solve for that missing piece. If you use the 6.7 instead, this number wouldn't have been off by much, but it would have been off. So be careful with that. And then we can substitute that in with our 1/2 base times height. But what I want to talk about, just like we figured out that there's a law of sines that helps us solve for a missing piece without two steps, there is a formula that lets us solve for the area without taking extra steps if we can recognize the relationship here. So from this up above, the 1/2 and the base are given, and the height is something we solve for. The height came from this on our triangle. So if we look at our triangle, the 7.6 was the A, and the sine of 28 was the sine of angle C. So with substitution, that would look like 1/2 the base, because those are parts of our triangle. The height is not necessarily part of our triangle, so that's what we can solve for. And that looks like A sine of C. That's what we did to solve here. And so the version you're going to see most commonly is they actually rearrange this, since multiplication is commutative, so that it's in alphabetical order. 1/2 A, B, sine of C. And here's what this means in a general triangle. If I have angles A, B, and C, and I know the angle C, and I know A, and I know B, then this is a side angle side situation where I have two sides and the angle in between them. If I have two sides and the angle in between them, I could draw in the height across from that angle somewhere, inside or outside the triangle, and use that version, or I can use this formula. So on this next one, all we have to check for is it side angle side. Do I have two sides and the angle between it? It has to be the angle in between. Remember from geometry, that's called the included angle. And if so, then I just have to use this formula. So for us, that's 1/2 first side, second side, and sine of the angle between them. And then we toss it in. For an area of about 59.8, and that's centimeters squared. Okay. If you have any difficult working through the homework, you will have to draw a few triangles, and if you struggle, come see me. But I do want to remind you, when you're looking at triangles, they don't have to be right triangles, and you're going to see for the first time today some instructions that deal with non-right triangles, so pay attention for that. Something that would maybe indicate that you are working with a right triangle is height or altitude. Okay, otherwise you can't make the assumption that it is right. And just come see me if you struggle on any of those.